time. An example we didn't do, but I'll do it if there's demand. People want to see another example of graphing a piecewise function? All right, so let's move along. So, today is kind of going to be a smattering of some different things you can ask about functions, different properties that you might ask of a function. You might ask about the rates of change of a function. As the input changes, how much does the output change? You might ask about notions of even and odd. You might ask about the symmetries that a function has. And finally, we'll hit the ideas of intervals of increase and decrease. Where is the function increasing? Where is it decreasing? And extrema, which is the plural of extremum, which is the one-word catch-all for both minimum and maximum. The techniques of mathematics should be agnostic as to whether you're finding a max or a min. They look so very similar. So, that's what we'll hit. The title is, in fact, the outline of the day. Let's go in order. So first, rates of change. So if you want to compute the average rate of change of a function, well, you can think in terms of the graph. So we know what, like, the rate of change of a line should be. Like, it should be its slope. The average rate of change of a function is the same as the average slope of the graph of that function. And let's just write down a formula. Well, maybe I'll write down the idea of the formula first. So if you have some x value x1, some other x value x2, you want to know what the average rate of change of that function over that interval is. Well, there's one point x1 f of x1. There's a single point x2 f of x2. Draw the straight line between them, in as much as you're capable of drawing a straight line, which in my case is, not. Compute the slope of that line. That's the average slope of the function over that interval. So we can write that down, is the slope of the straight line between those 2 points. So we can write down, we have a formula for average, for slope, right? It's change in y divided by change in x. Average slope is the change in the y-coordinate, which the y-coordinate is the function value. So maybe I'll write f for function value, divided by change in x. And then we'll just write it down, f of x2 minus f of x1 all over x2 minus x1. It's not below, it's to the right. So let's just do this computation in an example. Here is a function, x squared plus 1. So last semester, it was really annoying. It took me quite a while to figure out how to make it not going in and out of focus whenever I put my hand under the thing. Now I know which button to press to do that, but sometimes I'll forget because I don't see the screen. So if it keeps on going in and out of focus, just yell at me and I know how to fix it. So let's do a computation. Let's compute the average slope of this function over the interval from -1 to 2. And, well, we know what to do. It'll be the change in the function value divided by the change in the input values. And I know what the input values are. Now I just need to write down the change in the output values. Either by evaluating or by looking at the graph, what is f of 2 equal to? So, by looking at this graph, what can you tell me about f of 2? Yeah, cool. For a moment I was having trouble reading a graph and I was thinking that it was 3. But no, 5 is right. What's f of -1? 2. And then the denominator 2 minus 1 is 1. What's 5 minus 2? Cool. We've just computed the average rate of change of this function over the interval from -1 to 2. So now I'm going to have you do another. Tell me what the average rate of change of this exact same function is over the interval from -2 to 1. And I'm just going to be quiet for a few moments. You'll get a numeric answer. You'll check this numeric answer against... Oh, no. Before you do that, what have I done wrong? Because I have done something wrong. Yeah. 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 Anyway, when you think that I'd done goofed, chances are I'd done goofed. Anyway, how does that change the computation?
3/3, so 1.
Awesome. That's a silly mistake to make. All right. Now do that example. And my intent with these is to, like, once I hear some nice conversation that is people comparing answers with each other, then I know that the majority have it done. Cool. So what's the average rate of change of this function over that interval? I hear a -1. People get similar answers. So how many people did that by looking at the graph? How many people did that by looking at the formula for the function? Okay, maybe we'll real quick just do that both ways, and then I'll skip the next couple examples. So on the one hand, you could say, well, over this point, x equals -2. Draw that straight line. You have 2 points on it. You can compute change in y and change in x and go for it. The other strategy would be to write down the formula, delta f over delta x, f of 1 minus f of -2. That's going up the denominator this time. And we have a formula for what f of 1 is. F of x is x squared plus 1. F of -2 is -2 squared plus 1. And from there, that's just like some formula that you can now evaluate. 1 squared is 1, 1 squared plus 1 is 2. 2 squared is 4, 4 plus 1 is 5. Yeah, that works out to be -1. People feel pretty good about that? Yeah, so if you're given a graph, you can compute the average rate of change. If you're given a formula, of course you can do the same. Nice. So, I think well, we'll see. Would people like to see any of the remaining examples in the notes discussed? All right, then I'll skip by the rest of weights of change. Let's talk about the notion of even and odd. And I'll try to stick with that red and blue color coding for even and odd. So, let's see. Let's just give a check, see how many people do recognize the notation. So if I say a function is even, how many people already have some idea what I mean? All right, how many hands go up if I say, what do I mean when I say an even function? What do I mean when I say an even function?
Well, it starts and ends in the same direction.
It starts and ends in one direction. That's not super far from correct. it's getting there. Maybe I'll make the following objection to that. Would you want to call that an even function? I wouldn't. But it kind of like starts and ends doing the same thing. So that's the right idea. You want like symmetric behavior on either side. What are some other definitions people would want for the word even? Sure.
When a function and a negative version of that function both have the same output.
Yeah, a function and the negative version. Let's just make that precise. Like, what do you mean by the negative version?
Like f of 2 and negative f of 2 both have the same output.
Cool. That's also almost right. Yeah.
The inverse?
Inverse. What do you mean by inverse? Okay. I think we are, yeah.
It's f of x equals f of negative x?
Yeah, you have the negative in the wrong spot. Right? The function doesn't care whether the thing inside of the parentheses is the thing or its additive inverse. Cool. So a function is called even if the function at every input is the same as the function at negative that input. The function doesn't care whether the thing inside the parentheses has a positive or negative sign next to it. Graphically, well, okay, maybe we'll do that, then we'll hit the word odd. So if that's what it should mean for a function to be even, what would you want it to mean for a function to be odd? Yeah. They do not equal each other. So, there's one candidate. This isn't going to be quite what I'll want. So somehow, like, having an anti-property like this isn't sometimes so useful. But you might want, like, oh, even should mean you're not odd. But we won't want quite that. We'll want another sort of symmetry. Yeah.
Over the x-axis? As symmetry over the x-axis?
Nice. There's another candidate. And let's see what that would mean. So let's suppose you had a function that was symmetric over the x-axis, whose graph was symmetric over the x-axis. So there is a function. If I take that function and flip it over the x-axis, do I get the same thing back? I get this back. But in fact, if I had any non-zero value, that would get changed. So I think that's a little bit too strong. There's a different symmetry that we'll ask about. And this is all like slightly unfair, right? Like and I acknowledge that. Cool. So let's actually just write down what I want the word odd to mean. So a function is called odd if f of x is the same thing as negative f of negative x. Now that those two definitions are written, those look familiar, I hope, right? Okay, cool. And maybe I'll give an equivalent reformulation here. And it's clear those two things on either side of the word or mean the exact same thing. You just multiply both sides by -1. So that's what it means for a function to be even or odd. And now let's try to think in terms of graphs, whether these functions are even or odd. So this function, x squared minus 1, let's just plug in some inputs using the picture and see if it looks even or if it looks odd. So here's an input. X equals 3. It's not labeled any of the axes, so I can be pretty willy-nilly with what these values are. 3 squared is 9 minus 1 is 8. So there's a point 3 comma 8 on the graph. What if I plug in x equals negative 3? What will I get out of this function then? Also 8. In fact, does it look like this function cares whether the input you give it is positive or negative at all? Nah. Negative 3. The exact same y value. And the same thing all along the graph. If you take any input, any two inputs which are symmetrical over 0, you'll have the exact same y values. So you could take this, if you knew all the positive inputs, you know where they went. You could get all the negative inputs by reflecting over the y-axis. A function is odd in terms of the in terms of the graph if the graph is symmetric over the y-axis. So you can take the graph of the function, flip it over the y-axis, you should get the exact same thing again. Let's take a look at the graph of x cubed minus x right there. And that's same thing, plug in some numbers. Let's plug in 2 and negative 2 and see what happens. So on the one hand, by looking at the graph, is g of 2 going to be positive or negative? No, 2 is too big. Trouble with having no scale drawn. 1/2. By looking at the graph, should g of 1/2 be positive or negative? Negative, I think. And let's just go ahead and even compute what it will be. So let's see. 1/2 times 1/2 times 1/2 is an 1/8. Minus 1, I think that's negative 7/8. No. One half cubed minus 1/2. Get a common denominator. Negative 3/8. So 1/2 corresponds to the y value of negative 3/8. Let's look at what would change if I instead plugged in g of negative 1/2. So this 1/2 would become negative 1/2. What happens when you cube a negative? It just stays negative. Negative 1/2 cubed is negative 1/2 cubed. What would happen to that 1/2 if I replace the 1/2 with negative? An extra negative sign would appear, which would then pair with that negative sign in front of it. So basically all the negatives become positive, all the positives become negatives. So you're going to get exactly that same y value, but positive instead. Oh hey, and in fact that exact logic tells me this. The function does care if you plug a negative into it, and the negative just pulls out. So the same thing would happen no matter what x values you plugged in. If you change the sign of the input, the sign of the output changes. That's exactly what this says. And there's a reward for this sort of symmetry. You'll notice that all of these points, if I reflect them over the origin, I get the same value back. In terms of a graph, a function is odd if it is symmetric over the origin. All right, you'll notice that there's one last graph there. So by looking at that graph, tell me, is that function even?
Yes.
I hear a yes. Well, let's see. Let's take this and reflect it over the y-axis, see if we get the same thing again. So let's see, these bits that are going up like this will go over here. Here's what happens when I reflect over the y-axis. Is that the exact same function again? Okay, so it's not even. Right, that green graph isn't the same as the graph I started with.
Is it not even because it doesn't come all the way up? Like the shape of it looks even, right?
The shape of it looks odd, I think.
It looks odd.
Yeah, so notice this looks kind of like the graph that was there before I messed it up by drawing all over it.
The opposite way is the other one.
Oh yeah, it is. Instead of going from up to down, it goes from down to up. But an even function should either go from like up to up or from down to down. Notice this goes from down to up. So it has like opposite big picture behavior.
I think I'm getting confused.
That's right, I think
Between
I'm...
leads and degrees?
Hmm?
Between leads and degrees, are we... Aren't there 4 graphs that you choose between? If they go like this, or if they go like this? Or if they make an N? Or if they make... Am I getting confused now?
So, I think we're talking about topics that aren't directly related to this. So I think the buzzword you're thinking of is the one critical point, maybe. And there are 4 types of critical points you might see. And there are those.
Okay, and this is different than...
Yeah, they're related.
but different. Okay.
So let's check the same thing for this. Let's take a point on this original graph and reflect it over the origin. This point is on the graph. There it is reflected over the origin. Is that new red dot on the original graph? Nice. So that means it's not odd. So there's an example of a function that's neither even nor odd. Cool. How do people feel about this so far? Okay. So, we've seen checking if things are even or odd by looking at a graph. And maybe there's some spoiler in that, like, these are exactly the functions that were graphed on the previous page. Let's go through the motions of actually checking if these things are even or odd using the formulas. And maybe the way that I'll proceed is I'll check if, let's see, I'll either check if F is even or odd or G is even or odd, or H. And then I'll split you guys up and have you guys do the other. And people would prefer I talk through it back. G. H. Okay, a very mild preference for H. So let's check if H is even or odd by using the formula. So H of x is x cubed minus 1. Plug in negative x. There's negative x. It gets cubed. And then I subtract 1 from it. Let's simplify it out as much as we can, and then we'll go to the next line. What's negative x cubed the same as? What can I do with that negative sign? Let's see, it'll be like a negative times a negative times a negative. 2 of the negatives will cancel, and I'll be left with 1. So that's the same as negative x cubed, and then minus 1 will just stay on its own. I don't see any other obvious simplifications to make. So maybe we'll go to the next line, see if they're the same. Negative h of negative x. Negative h of x. Yeah. Oh, maybe we'll check this right now. Is that thing in green the same as h is? No, they differ by like a minus. The x cubed has a minus sign, and here it doesn't. So this function is not even. Next, let's evaluate negative h of x, because if h is odd, then this should be the same as that. Well, let's do that. So that'll be negative, big parentheses, x cubed minus 1. So if you saw that and you wanted to simplify it, what would you want to do? Yeah. Let's distribute that negative. We'll get negative x cubed minus minus 1 plus 1. Are these two the same? Yeah, so these two are not the same. Which means this thing is not odd. Alright, so there's a function that's not even and not odd. Here's what I'll have you guys do real quick. Look at the formula for that. Tell me if it is even or odd by evaluating negative f of x and f of negative x. Same thing for g. Someone's getting a call. Cool. So, maybe I'll ask about evenness first. So the function f. Even or not even? Is it even? Is it not even? People want more time? People want me to talk through the thing to me. Okay, oh, yeah, it's even. Which you might think makes the following question silly, but it's not totally silly. Is the function odd? Well, no, I want to do G. Is G even? Folks for yes? Anyone for no? Anyone for I want more time to do the computation? Okay. Do you want me to talk through the computation for G? Okay, let's do it. Let's plug in negative x for x and see what happens. G of negative x, so that means I should replace every x with negative x. So there's going to be a negative x that gets cubed minus negative x. And then you just have to like simplify everything out. Negative x cubed, what happens to a negative sign when you cube it? Yeah, there's like a single negative that pluses instead of 3 of them. Same as negative x cubed. And then I see minus minus x. What can that become? Plus x. There's no more simplification to do. So now you look at this. You look at that. Do those two formulas look the same? No, they're different, right? This has a negative sign in front of the x cubed. That doesn't. This has a positive sign in front of x. That has a negative sign. Those two things are not the same, so it is not even. Is G odd? Folks for yes? Anyone for no? Should I talk through a computation? Nice. I saw A had none, so let's do it. So negative G of x will be negative x cubed minus x. Then we distribute. And a function will be odd if these two are the exact same. Are those two the exact same? So this is odd. Oh, and I skipped the question, is f odd? Is the function f odd? Folks for yes? Folks for no? Cool. And maybe I'll pose this as an interesting thing to think about. There is only one function which is both even and odd. And screensaver. What is that function? So there's a thing to think about, if you want to. So let's, that is currently none of these three functions. So the next thing are the ideas of intervals of increase and intervals of decrease. And maybe in order to motivate thinking about this, the definition that I will write down, I'll start by just asking you, where is it increasing and decreasing to convince you already know the answers. So let's, I don't know, try to begin. Let's take like that x value. Come on, correctly. If I were to ask you, at that x value, is the function increasing or decreasing, what would you want to say? Yeah?
Increasing.
Increasing. Right? Kind of as the x values go left to right, the y values are going up. So as x's go left to right, the y values are going up, and then it stops going up at some point. Just like there-ish. I don't know, negative 1.2-ish, maybe that is? You can't say very much precise on this particular graph. We'll say something more precise in a moment. So it looks like all the way from negative 2 to negative 1.2-ish, this function is increasing. And then it switches to decreasing. Or it sure seems like it does. So it starts decreasing, it's going down, it's going down, it's going down. And there's some point where it turns around. If this x value is negative 1.2, then where do you think that x value is? 1.2. And in fact, like, this function is odd, I think. So it should have like exactly the opposite behavior on either side. So this place where it turns around should turn around again. And then it starts increasing again. And I'm stopping at 2 because there are solid dots decorating the endpoints of the graph, so this function I'm saying isn't even defined yet. How do people feel about that? Apparently people, because I saw a few looks of consternation when I put those brackets at either end. Some people would rather have seen parentheses at the other side of this instead of brackets. Oh, okay. There is an argument, right? At that endpoint, it doesn't really seem like it's increasing or decreasing, it's turning around. So there's an argument for that. But I'm going to write down a definition for what it means to be increasing on an interval, which will mean I have to include this. So what does it mean for a function to be increasing on an interval? It means for all inputs, I don't know, a and, no, x1, x2. x1 and x2 in that interval. If x1 is less than x2, then f of x1 is less than, I'll say less than or equal to f of x2. Does that seem to capture the same thing as you knew should be? So let's parse that out. That says, if you take any two inputs in the interval, if this input is to the left of that input, then the resulting output will be below that input. So as the inputs go left to right, the outputs go up. Similarly, a function is called decreasing if for all inputs x1 and x2 in that interval, if x1 is less than x2, then f of x1 bigger than or equal to f of x2. How do people feel about that? Feel pretty okay? And if you take that definition, then you do have to include the endpoints over that whole blue interval. If you take any input that's less than that endpoint, then the y values will satisfy the inequality that they have to be increasing. That being said, maybe I'll say this. If you happen to be writing up things like homework, and you decide to make a different conventional choice and exclude endpoints from intervals of monotonicity, I'll still be happy. I won't worry about endpoints when it comes to intervals of increase and decrease, because there is an argument to make some different definition. People feel okay? Cool. So let's ask one other question. By looking at this graph, at what inputs, so we'll specify inputs only. At what inputs does it look like this function pawns around, changes from increasing to decreasing? Yeah.
Negative 1.2 and 1.2.
A turning point of a function is an input where the function changes from increasing to decreasing or decreasing to increasing, which I'm short on space, so I'll summarize decreasing to increase with the word conversely. So, I've gone to some portion of the class in pre-calculus that's seen some amount of calculus. So, how many people have seen some Calc 1 in the past? So, do you remember the term critical point? So, that term is closely related to the idea of a turning point. If you like, what we're about to do will be related, well, what we'll do after this page will be related to that relationship. So up there, we said the turning points are around plus or minus 1.2. Do you think we could do better if we had a better graph to work with? Yeah, so let's get ourselves a better graph to work with. Let's try to find the turning points of this same function by looking at a better graph. By the magic of television, I have a better graph pulled up. So I know there should be a turning point around that x equals negative 1.2. Well, so let's zoom in on that x value of negative 1.2. And I'm not saying this is like the only tool to use, but this is a tool that I can use conveniently. So I'll pick some window that contains negative 1.2. Let's see, those y values are like around 3-ish. So by just looking at this much of the graph, you can see the grid down there. If I asked you now about where is the turning point of this function, where would you tell me? Negative 1.15-ish. And there's nothing deep there. If you wanted to do better than negative 1.15-ish, what would you do? Zoom in again. Yeah. And I'm, and there's another one at positive 1.2, which we could find by like zooming in again. Let's take advantage of the fact that this is an odd function, so it has like the exact opposite behavior on the opposite side of the x-axis. So what do you think the other turning point is? 1.1. Yeah, positive 1.15. And so the sales pitch from calculus is calculus gives you a very good tool to find these turning points on the nose exactly. We won't try to do that because this isn't a calculus class, this is a class on pre-calculus. But those things are important, and the tools to really find them on the nose precisely, that is a thing that you'll do next semester when you take calculus. And I have 8 minutes. This is okay. Let's talk about extrema. So here is the graph of a function. It looks like a piecewise function where the pieces are made out of linear things. You could write down a formula, but it'd be a pain, all right? Let's not. Let's just look at this graph and try to read things off. What is the maximum value this function takes? What's the biggest output value you see? 5. That's right. If you like convincing you, again, that you already know what the definitions are. What input results in that maximum value? Yeah. So you can see here, this is the biggest y value I see. What is the input that produces it? -5. Similarly, you can compute the minimum value. It looks like there's a minimum right there-ish. Looks like that's a y value of 1, 2, 3, 4. And the input that produces it is x equals 2. Those things make sense? So a lot of times in mathematics, mathematicians like to define local versions of things. And whenever a mathematician talks about a local thing, that mathematician is just saying, well, what happens if you're only allowed to look at inputs that are like really, really close to some input? So let's see if I can, how close can I zoom? Okay, so that's as close as I can, so that's useless. So on the previous .cam, you could get into like 100x magnification or something, and it got really grainy, but the picture looked nice. So let's suppose that let's look at this picture right here. Suppose that you were only allowed to look at that small viewing window. If you were only allowed to look in that small viewing window and couldn't see anything else, what type of value would you think that was? A minimum, right? If you can't see any of the rest of this graph, and if I could zoom in better, I could just stop you from seeing it, but I can't. This is an example of a local minimum. Are there any other points where if you just drew a really small box around that point, you would think that that point is max or min? Yeah, it looks like up here at 0, 2. It looks like a maximum or a minimum? Looks like a maximum if you only saw that much. So it looks like there's a local maximum at x equals 0, a local minimum at x equals, 1, 2, 3. And maybe another one right there. Nice. So you'll notice that sometimes a local minimum is an actual honest-to-God minimum. It doesn't need to be. The actual honest-to-God maximum might not be a local maximum. It might be an end. So let's just finish this off, write down these definitions. An input C is called a global maximizer for a function if the output at C is at least as big as every other output. That seems like a good definition. That seems so. How many people would want that to be like a strict inequality instead? Okay. Well, no one did, but I'm going to tell you why that's something you don't want to do regardless. So imagine you saw a function that looked like this, with both of those being exactly the same height. If you didn't have this equal to option, then you wouldn't be allowed to call either of those a global max, because there would be another input which achieves the exact same output. So you're allowed to achieve the maximum more than once. Minimum, same thing, but the inequality switched. And input C is called a local maximizer if f of C is bigger than or equal to f of x for every, let's just say input x close enough to C. So if you're only allowed to look at inputs that are close to the input that you're looking at, then is that the biggest output you see? That's what it means to be a local max. And Same thing for local min. So let's go back to this function, x cubed minus 4x, which is graphed on the previous page. Right, it was this function. What does it look like the maximum value this function takes is? 3. What x value achieved it? Yeah. Oh, yeah, sorry. So by flipping back to the graph, what was the input that gave you that output? Negative 1.2? And maybe I'll say that that was a local and a global max. And maybe that's good enough for now in order to highlight this point. That's the exact same as where the turning points were, right? Turning points tend to be places where local maxima are. So the logic of calculus that helps you maximize things is helps you find turning points, which are local extrema, which are often honest-to-God extrema. So that's how you can maximize things using calculus. Not that we'll do that this semester. So I'll stop there. That being said, I won't go anywhere, so you should be packing. If people have any questions they want to ask, now is a great time.